Hello and welcome to this next example video. We're going to see an example of using change of variables for integration over spherical coordinates in this video. So what we want to do in this video is we want to integrate over a region that can be conveniently described using spherical coordinates. Specifically, we'd like to integrate over all x in r to the third such that all components of the vector x are non-negative, and such that x1 squared plus x2 squared plus x3 squared is less or equal to 1. So what we actually do here is we integrate over part of the unit ball. So this here is a description of the unit ball, means the norm of x squared, this is the norm of x squared basically, is less or equal to 1. And that's just the description of the unit ball. So what we're doing here in effect is we're integrating over this ball here. And more specifically, we're only integrating over all x's with strictly non-negative values. So it's not the whole ball that we are going to integrate over, but just the part of the ball that is here in the positive orthant. So that is 1/8 of a unit ball, actually. And to not complicate things further, what we want to know in this example is just the volume of that area x. So to get the volume of x, we integrate the one function over x. Again, we're going to not do this in Cartesian coordinates. Instead, we're going to use polar coordinates for that. And we are in 3D space, so there's basically a choice of two possible polar coordinates. The one is the cylindrical coordinates, where we add a height axis to the usual two-dimensional polar coordinates. The other is the spherical coordinates, where we add an angle, an elevation above the x1, x2 plane. And that is what we are going to use here, because that is more suitable to describe spherical bodies like a sphere. Okay, so we're going to use spherical coordinates. Briefly recall how these look. So if you want to describe a point in 3D space using spherical coordinates, what we do is basically we use polar coordinates in the x1, x2 plane. So we have an angle phi and a radius r. And then we elevate this point above the x1, x2 plane, or below the x1, x2 plane, with another angle. That angle here, that's going to be called psi. So this is the angle psi. And here's our point. This length here is then the radius of that point. So that's the idea of spherical coordinates. We've talked about the transformation for those already. So if we have a point r, phi, psi in spherical coordinates, then the corresponding Cartesian coordinates can be computed as r cosine phi times cosine psi, r sine phi times cosine psi and r sine psi. So that is the transformation that we need here. Now, as usual, for the change of variables, the first thing we need to do is we need to compute the Jacobi matrix of the transformation and then its determinant. Okay, so we want the determinant of the Jacobi matrix of G of R phi psi. And so let's see what this Jacobi matrix is. If we first differentiate all the coordinates with respect to R, we always have this R here in front, so that just vanishes for the differentiation, and that means we get cosine phi, cosine psi, sine phi, cosine psi, and sine psi for the first column of the Jacobian. Then we differentiate with respect to phi, and we have phi appearing here. So that means for the first row we get minus r sine phi cos psi. For the second row we get r cos phi cos psi. And for the third row we get 0 because there's no phi in there. And finally we differentiate with respect to psi, and that appears here. So for the first row we again get minus r cos phi sine psi. Similarly for the second row we get minus r sine phi sine psi. And for the third row we get r cos psi. And now to compute the determinant here, we are going to expand with respect to the third row, because there's 0 in that third row, so that hopefully makes things a little more convenient. So the first term is a minus 1 to the row number is 3, the column number is 1, so 3 plus 1. Then we have this element sine psi here. And then we have the determinant that remains if we remove the last row and the first column. So this part here, that's what remains. Okay, so times this determinant here of minus r sine phi cos psi, r cos phi cos psi, minus r cos phi sine psi, and minus r sine phi sine psi. And then as the next element we have this r cos psi here. So that's in row 3, column 3, so we get minus 1 to the 3 plus 3. We then have this element itself, r cosine of psi. And then we need to multiply with the determinant that remains when we remove the third row and the third column. So the determinant of this green part here. So what is left is determinant of cosine psi, cosine phi cosine psi, sine phi cosine psi, and minus r sine phi cosine psi, r cosine phi cosine psi. Okay, so let's evaluate the result here. Minus 1 to the fourth is plus 1, so we have sine psi plus sine psi here. This orange determinant, this becomes, let's see, an r squared sine phi squared, and we have sine psi cos psi plus r squared cosine phi squared times sine psi cos psi. And for the second part, minus 1 to the 3 plus 3 is minus 1 to the 6, so that's plus 1 again. So we have r cosine of psi, and this determinant here. Now this is r cosine of phi squared cosine of psi squared plus r sine of phi squared cosine of psi squared. Okay, so let's see what terms we can take out of these expressions here. So in this first part here, we have an r squared and we have a sine psi cos psi in both terms. So let's take that out. So that's r squared sine psi squared cos psi. And then we're left with sine squared phi plus cos squared phi. That will be 1, as you know already. And for the second part, we have this cosine squared of psi, and we have a radius r that we can take out. So we have r squared cosine psi to the third. And again, what remains is cosine squared phi plus sine squared phi. This is 1, and this is 1. So we are left with r squared cosine psi sine psi squared plus r squared cosine psi squared. So as you can see, we can take out r squared cosine psi and then get sine squared psi plus cosine squared psi, and again this is 1. So what remains in the end is r squared cosine psi. So finally, that is the determinant of the Jacobian for this transformation from spherical coordinates. And now we can make use to evaluate the integral, that here. Remember, what we wanted to integrate was this area x here, the positive eighth, if you want, of the unit ball. Now first we need to describe that in terms of spherical coordinates. And that can be easily described as r phi psi, like this. So obviously the radius is still between 0 and 1. Phi, what about phi? So we're talking about all angles in this plane here. So that is phi between 0 and pi over 2. And for psi, we're talking about all angles in this region here. So this is psi between 0 and pi over 2 as well. Okay, so phi in 0, pi over 2, and psi in 0, pi over 2. So that's our domain D. And with that, we get the integral of 1 dx over x is the same thing as the integral of d, 1 of g of r phi psi, but 1 of anything doesn't change. So all we have to do is we have to multiply this with the absolute value of r squared cosine psi, and then integrate this dr phi psi. So what this amounts to is a triple integral. We integrate r from 0 to 1, phi from 0 to pi over 2, and then psi from 0 to pi over 2. Now in this area, where psi is between 0 and pi over 2, the value of the cosine, remember the cosine, that looks like this. Here's pi over 2, here's 0. So the cosine in that area will be non-negative. That means we can forget about the absolute value here. So we can just integrate it over r squared cosine psi d psi d phi dr. And that's easily done. So we have this integration over r. We can move the r squared out here. Then we have the integral over phi. And the integral over psi, we can evaluate that right away. So the integral of the cosine of psi is sine of psi, psi from 0 to pi over 2. D phi dr. So what we get here is, well, the sine of pi over 2 is 1. The sine of 0 is 0. So we have 1 again. D phi dr. Oh, I forgot the r squared here. So let's integrate this phi part. Obviously, that's just the integral over 1. So the integral is phi from 0 to pi over 2 dr. And that means what we have here is just pi over 2 minus 0. So we can just take out this factor pi over 2 and then integrate the r part. And that is r to the third over 3. All from 0 to 1. So what we get in the end is pi over 2 times 1 over 3. And that is pi over 6. Okay? So this is the volume of this 1/8 of the unit ball. And if you happen to know the volume formula for the ball, you will easily be able to verify that this is actually correct, or let's say in tune with what you already know. Okay, this concludes this example on spherical coordinates. Thank you for your attention, and I'll see you in one of the next videos.